Hello everybody. Today I'm going to explain what is a high-pass filter. Well, a high-pass filter is a filter that accepts all the signals with a frequency greater than the cutoff frequency and rejects or attenuates all signals with frequencies lesser than the cutoff frequency. It is just opposite to that of a low-pass filter. The exact frequency response of a filter depends on the filter design. And in the audio world, a high-pass filter is often referred to as a low-cut filter or a bass-cut filter because it cuts all the low frequencies below the cutoff frequency. Alright, similar to a low-pass filter, there are two types of high-pass filters. One is the ideal high-pass filter and the other is a real high-pass filter. Clearly, the ideal filter doesn't exist in real life, but it's just worth mentioning it. So what is an ideal filter? An ideal filter is one that has full transmission in the pass band and complete attenuation in the stop band, and the transition is an abrupt one. So what it means is this filter, especially the high-pass filter, accepts every single frequency above the cutoff and rejects every single frequency below the cutoff. So for example, if the cutoff frequency were 1000 Hz, this high-pass filter will accept every single frequency from, say, 1001 Hz and above and reject every single frequency from 999 Hz and below. So the frequency response is a rectangular function and it's a brick wall filter, meaning it's just the transition is just a straight line. Now we'll observe a more realistic high-pass filter. Alright, a real high-pass filter is obtained by approximating the ideal filter by truncating and windowing the infinite impulse response to a finite one. So as you can observe in the picture, the transition is no longer a straight line. It's no longer a brick filter anymore. Rather, it's a smooth transition due to the application of a window. So typical windows used are Hamming, Han, and flat top, and there are a lot more. So what we can conclude from this filter is that the filter doesn't have a brick wall nature, but it rather, accepts even some frequencies below the cutoff. Alright, similar to low-pass filter, there are two major types of circuits that achieve the high-pass filtering. One is the capacitive high-pass filter, also known as the RC HPF because it uses a resistor and a capacitor, and the other is an inductive HPF or an RL HPF because it uses a resistor and an inductor. So the resistive capacitive type, the RC HPF, blocks frequencies below the cutoff, whereas the RL type shorts out frequencies below the cutoff. Alright, let's study the RC HPF type first. So as I explained earlier, RC is constructed using a resistor and a capacitor. So the capacitor is in series with the input signal and the resistor is parallel with the input signal. We'll look at the circuit diagram in a bit. So the equation for a cutoff frequency still remains the same. It is F equals 1 over 2 pi times R times C. So R is the resistance measured in ohm, C is the capacitance measured in farad, and F is the frequency measured in hertz. Let's look at the circuit diagram. Alright, this is a circuit diagram for an RC type. So on the left you have the input signal and then there is a capacitor in series with the input signal. After that there is a resistor in parallel with the input signal and then there's the output. So if you notice clearly, for the low pass filter the same circuit was used but the positions were swapped. So now let's understand how does this work in achieving high pass filtering. Alright, let's understand the working principle of an RC circuit high pass filter. To preface, a capacitor is a reactive device which offers varying resistance to signals of different frequencies passing through it. Especially, it offers very high resistance to low frequency signals, but offers low resistance to high frequency signals. Due to the low resistance, the high frequency signals pass through the capacitor. When the signals are coming from the input, and since the capacitor is connected in series with the input, they just pass through them and they are directed as the output. On the contrary, due to very high resistance, low frequency signals aren't even able to enter the capacitor and hence they are blocked right there. So what is in the output is definitely high frequency signals and hence the high frequency filtering has been achieved. Alright, now let's talk about RL circuit high pass filter. So as the name suggests, it's constructed using a resistor and an inductor. The inductor is in parallel with the input signal and the resistor is in series. So the cutoff frequency is still the same as the low pass filter equation, R over 2 pi L. R is the resistance measured in ohm, L is the inductance measured in Henry, and F is the frequency measured in hertz. Let's look at the circuit diagram for an RL circuit. Alright, this is a circuit diagram for an RL type high pass filter. So on the left, there is an input signal, then the resistor is connected in series with the input signal, and an inductor is connected in parallel with the input signal, and then there is the output. So if you compare this diagram with a low-pass filter circuit, the resistor and the inductor have swapped positions. So this is the construction. Let's look at the working principle of such a circuit and how it achieves high-pass filtering. Alright, let's understand the working principle of an RL circuit high-pass filter. To preface, inductor is also a reactive device similar to a capacitor which offers varying resistance to signals of different frequencies passing through it. But the only difference is, compared to a capacitor, an inductor offers very high resistance to high frequency signals and very low resistance to low frequency signals. Due to the low resistance, low frequency signal easily pass through the inductor after passing through the resistor, whereas the high frequency signal, due to high resistance, they are directed toward the output. They don't even enter the inductor. So in this case, the high frequency signals have been shorted out and directed to the output. And hence, the high-pass filtering has been achieved since all the frequencies at the output are above the cutoff frequency. Alright, this is a graph of a first-order high-pass filter. I have chosen the cutoff frequency to be 5000 Hz, and this is how it looks like. Alright, let's talk about higher-order filters. Now, what is an order of a filter? The order of a filter is determined by the number of reactive elements, such as the number of capacitors or inductors in the circuit. In today's video, we've been talking about a high-pass filter with one capacitor and one inductor. Now that classifies as a first-order filter. Now there are higher-order filters which have more reactive elements. For example, if a filter has two capacitors and two inductors, that is referred to as a second-order filter, and so on. So what is the advantage of a higher-order filter? Well, they have advantages like they offer more phase shift, and most important, they offer greater attenuation compared to a first-order filter. So the order is directly related to the slope of the frequency response curve. As you observed in the first order curve, it had a lesser slope. Now let's look at a fourth order filter which has a much steeper slope because it's a fourth order filter. Alright, this is a fourth order high pass filter. Look at the curve. It's much steeper compared to the first order. Since it's a fourth order filter, it's offering greater attenuation compared to the first order. Even the cutoff frequency is still the same. It's still 5000 Hz. Alright, now I'm going to be demonstrating the effect of a high-pass filter by using a noise signal. I'm going to be using a white noise. To give a preface, a white noise is a random noise signal having equal intensity at different frequencies, giving it a constant power spectral density. What it means is every single frequency from 20 Hz to 20 kHz is being played at the same time and at the same amplitude due to the constant power spectral density. So I'll be playing the pure white noise first, and then I'll be applying two filters. One is a first order 5000 Hz high pass filter, and the second is a fourth order 5000 Hz high pass filter. Alright, I hope you heard the white noise, pure white noise, and the filtered white noise. What we can conclude after listening to the filtered white noise is that it sounds a lot more hissier, because it has more high frequency content and devoid of low frequencies. Alright, let's look at some application of high pass filter. So they're predominantly used in microphones. So to preface, microphones are devices which record the sound signals. So they need both AC and DC signals in order to work. So DC is required to power them up and operate the microphone, whereas AC is required because they are the signals that are recorded as a human voice or music. So DC is direct current and AC is alternating current. So what is the application here? So it is important to keep the AC signals free from the DC noise because the DC signals are only used to power the microphone. They need not be present in the AC signal. In order to keep the AC signals free from the DC noise, a high pass filter is used, which blocks the DC and only allows the AC to pass through. Another application is digital high-pass filter, which are used in digital softwares like sound analysis, mixing, and editing. They follow the same principle of a physical high-pass filter, and they find applications in music editing, mixing, and sound analysis. Alright, thank you for watching this video. I hope you enjoyed it. If you have any questions, hit the comments. I'll be sure to respond. Alright, thanks a lot and have a great day.